For years, it was nothing more than a whisper in the data, a faint trace of light buried in the noise of the cosmos. Astronomers had nearly dismissed it as a glitch, another phantom blip lost in the background, radiation of deep space. But that flicker wasn't random. It was the first glimpse of something that would soon shake every assumption we've held about what drifts between the stars. They call it 3I/8-less, and NASA has just done the unthinkable. They've predicted its arrival down to the exact day. What they found isn't merely another comet streaking past our solar system, it's an interstellar object, one that wasn't born under our sun, and it's moving toward us with a precision that's starting to make scientists uneasy. Think of it, an ancient traveler from a completely different star system crossing the infinite dark, heading into our celestial neighborhood for the first time in recorded history. Why is it coming? What secrets does it carry? And what does it mean that NASA's own simulations show this object cutting through our solar plane in a trajectory unlike anything ever observed before? 4 years ago, 3I/Atlas was barely a dim echo in telescope data. Now it's a focal point of global attention, a countdown ticking toward what may become one of the most closely watched cosmic encounters of the century. The agency's scientists at the Jet Propulsion Laboratory have narrowed its path with almost frightening accuracy. Every new observation refines its position, every photon caught by distant observatories adds weight to the growing sense that this isn't just a routine event. The previous visitors, Oumuamua in 2017 and 2I/Borisov in 2019, both came and went, leaving behind more questions than answers. But 3I/Atlas is different. Its light curve, its velocity, its angle of approach, all of it suggests a composition and behavior outside known categories. As NASA teams around the world synchronize their instruments for what they're calling the interstellar observation window, the rest of us are left staring at a simple but profound truth. We are about to witness the third ever confirmed visitor from beyond our solar system, and this time we're ready. Or are we? Because while scientists are busy calculating orbital inclinations and solar interaction models, others are asking deeper questions. What if 3I/Atlas is not just a piece of rock and ice, but a message, a fragment of another world's history or technology? It might sound far-fetched, but it's precisely that edge between fact and possibility that keeps humanity's eyes locked on the sky. And now, with its arrival window officially confirmed, the countdown isn't just scientific, it's existential. We're not looking at a hypothetical anomaly anymore. We're watching something real, measurable, and inevitable. As of now, the data points converge into one stark conclusion. This object is coming sooner than expected, and the world's top observatories from Hawaii to Chile are already adjusting their lenses to catch its light. Whatever 3I/8-less turns out to be, it's not just passing by unnoticed. It's rewriting the playbook of interstellar science, one frame at a time. Once NASA confirmed 3I/8-less's interstellar origin, the race to decode its trajectory began. At first, the data seemed inconsistent, a faint cluster of light points shifting slightly night after night, recorded by telescopes from opposite sides of the planet. These weren't crisp images of a glowing comet tail, but subtle changes in brightness, a cosmic heartbeat flickering through the black. The challenge was immense, tracking an object so distant that even a fraction of a degree in measurement could distort its entire flight path. To solve it, scientists turned to parallax, a technique as old as astronomy itself. By observing the same point in space from two different locations, Hawaii and Chile NASA's teams measured how 3I/8-less appeared to jump against the background of stars. That minute shift multiplied by millions of kilometers revealed something extraordinary. Its velocity and trajectory didn't match any known solar object. It wasn't orbiting the sun. It was just passing through fast, clean, and indifferent. The Jet Propulsion Laboratory ran thousands of simulations, layering every observation into high-fidelity orbital models. Each night, the range of uncertainty shrank. From a fog of potential flight paths, a single razor-sharp arc began to emerge. When the model stabilized, the results stunned even the experts. NASA could now predict 3I/Atlas's closest approach within a margin of just a few hours. That kind of precision for an object from another star system bordered on impossible. Only 2 additional nights of observation had made the difference, a testament to the power of global collaboration and the evolution of modern astrophysics. But with precision came a new set of questions. Why was 3I/8 traveling at this specific velocity, slower than Borisov, yet faster than any long-period comet? Why did its radiant, the point in the sky from which it seemed to originate, lie closer to the galactic plane? Some suggested it meant 3I/Atlas wasn't ejected from a single distant star, but rather drifted from the interstellar medium itself, the diffuse material between star systems. That would make it not just a visitor, but a piece of the galactic bloodstream, a relic of star birth and destruction scattered across light years. To confirm it, NASA and the European Southern Observatory began a joint observation schedule. Ground-based telescopes would capture visible light, while space-based observatories, like the James Webb Space Telescope, prepared to read its infrared spectrum. Every wavelength carried clues, the chemical fingerprints that could expose where this traveler was born. Scientists were on the verge of turning a mystery into a map of cosmic history. Yet, beneath the excitement lurked a growing unease. For all the data they had, there was one question they still couldn't answer: what was inside 3I/8, a frozen core of volatile ice, a rocky body scarred by radiation, or something no model had yet imagined. As more data poured in, the mystery surrounding 3I/8 deepened. Spectrographic readings hinted at irregular brightness fluctuations, subtle but undeniable. For a typical comet, these would signal jets of gas escaping as sunlight vaporized frozen material. Yet for Atlas, the rhythm was uneven, erratic, as if the object was breathing in a way no comet should. Astronomers proposed competing theories. Some argued it was an icy fragment whose crust had hardened after eons of cosmic radiation, sealing volatile gases beneath. Others believed it was more akin to an asteroid solid, and dense with a reflective layer disguising its true nature. If the latter proved true, it would overturn long-held models suggesting that interstellar visitors are primarily ice-rich, fragile, and short-lived. A stony interstellar traveler would imply that alien solar systems produce debris with far greater variety than previously thought, from metallic shards to dust-fused monoliths. That possibility electrified the scientific community. It also revived comparisons to Oumuamua, the cigar-shaped enigma of 2017, whose strange acceleration had led some to speculate about non-gravitational propulsion. Could Atlas display similar behavior once it neared the Sun? If so, we might be standing on the brink of observing another phenomenon that defies classical physics. As NASA's and ESA's teams prepared for the upcoming Mars Flyby corridor, astrophysicists began modeling how solar radiation would strike Atlas's surface. Its inclination angle was unusually steep, a trajectory cutting through regions saturated with solar wind and charged particles. The interaction could trigger volatile outbursts or cause brief flashes of light visible even to amateur astronomers. In the labs, scientists simulated these effects, predicting potential green flash events, surges of spectral energy reflecting off ionized material. To the public, it might look like a distant emerald spark in the night sky. To researchers, it would be a data goldmine. Still, others urged caution. While enthusiasm swelled, skeptics reminded that interstellar objects have a way of subverting expectations. Oumuamua had confounded models. Borisov had conformed to them. Atlas might do both or neither. But beyond the equations and debates, there was a deeper fascination. Every such encounter is a snapshot of galactic evolution. Inside Atlas's grains of dust may lie elements forged under a different sun, shaped by different magnetic fields, influenced by conditions that no probe or telescope has yet measured. That makes it not just a rock, but a time capsule one that could tell us how matter behaves outside our cosmic cradle. For planetary scientists, this is more than a headline. It's an unprecedented opportunity to refine the blueprint of how worlds are born. As the James Webb Space Telescope aligns its infrared sensors toward Atlas's approach, window researchers prepare to decode its chemical identity. Ratios of water carbon monoxide and silicate dust could reveal whether Atlas formed in an icy ring of a young system or in the hotter debris belt of an ancient star. Each molecule is a clue in an interstellar crime scene pointing back to a place that may no longer exist. But what happens if those readings show something unfamiliar? A pattern no catalog can match? Would that mean we've discovered a new class of cosmic body, or that our understanding of interstellar chemistry is fundamentally incomplete? That's the tension gripping every astronomer watching the countdown unfold. This isn't just a flyby. It's a test of how much we truly know about the universe beyond our sun, and how much we still don't. As the final weeks of observation draw near, the world's telescopes lock onto a single moving point across the void, 3I/Atlas, now bright enough to register in public sky maps. Its motion through the inner solar system has become a global event, with data streams flowing in from observatories on nearly every continent. The James Webb Space Telescope begins its infrared scans, searching for subtle variations in temperature and composition, while ground-based arrays capture optical changes that could mark jets or outgassing events. Each detection is a fragment of a larger narrative, the story of a traveler shaped by forces older than our planet. In laboratories from Pasadena to Paris, scientists run real-time comparisons between Atlas and its predecessors. The differences are striking. Its albedo higher than Borisov's, its density lower than predicted, and its trajectory slightly skewed by what some describe as microthrusts, the tiny nudges caused by uneven gas release. These irregularities hint that beneath its crust Atlas might still harbor volatile material frozen since the dawn of another star. The data points form a pattern both familiar and alien. One moment it behaves like a comet, the next like an asteroid, and sometimes like neither. The result is an object that refuses classification, forcing astrophysicists to rethink where the boundaries between rock ice and cosmic artifact truly lie. In a way, it's a reflection of ourselves, always searching, never fully certain. But beyond the science, there's a collective awe. For the first time, humanity is not caught off guard by an interstellar visitor. We are watching prepared instruments, tuned eyes steady, and in doing so we are taking part in something rare. A moment of cosmic connection, a brief handshake between two worlds that will never meet again. When 3I/Atlas completes its solar pass and drifts back toward the interstellar dark, it will leave behind more than just measurements and charts. It will leave perspective proof that the galaxy is not a distant abstraction, but an active system that touches us literally through objects like this. Each interstellar visitor is a messenger, a reminder that our solar system is not isolated but woven into the fabric of something far larger. As NASA compiles the final observations and the countdown resets for the next unknown traveler, one question lingers, the same question that has haunted humanity since we first looked up at the stars. Are these fragments merely debris from the birth of distant suns? Or could they be the remnants of something once alive, intelligent, or even intentional? The answer for now remains hidden in the cold silence beyond the heliosphere.